All right. So midterm on the 21st, next Monday. So please come to class. If you can come early, that'd be nice. If you have class before this, that's okay. Just be here by 10:30. Once everyone's here, we'll get started early. Um, I have the example midterm on, or not example, it's last year's midterm uploaded for this week's lecture. The solutions has been uploaded, but it's not available until Wednesday. So I'm just encouraging you to all try the midterm before you look at the solutions. That'll become available on Wednesday. Homework due this Thursday. There will be another homework assigned, but I'll make this homework really light and relatively chill, so you don't have to worry too much about it. Shouldn't um, take too long. And all material covered from today onwards will not be on the midterm. So we ended on second order systems. So anything beyond second order systems, so like high order systems, will not be on the midterm. Uh, Basically, lecture slides like lectures 1 through 4 up to this page will be fair game on the midterm. And I'll make an announcement about that, about the sections that will be covered on the midterm. Currently, format will likely be 3 problems. I have yet to write it. And open notes, open calculator, no internet, no MATLAB, no Python, no computational software. And that's that. Any questions before we get started? Yeah. Oh yeah. Yeah, your notes can be on your iPad. If you have notes on your laptop, that's fine. You can bring your laptop, look at notes. Just don't use internet, please. And if you want to look at the textbook, if you have the online textbook, PDF textbook, that's fine too. You can bring that on your laptop or tablet. All right. So on Thursday, oh, and one last thing, I will have a review session on Thursday. I'll do a review of all the material that will be covered on midterm one. It'll just be a very, very broad overview summarized into one lecture material, like lecture slide. I'll probably release that later this week, such that you can print that out as like a cheat sheet, like a concise cheat sheet, so you don't have to go through dozens of pages of notes. Okay, so on Thursday we finished some general definitions on generalized second order systems, and we're going to be moving on to higher order systems. Maybe to just recap real quick on first order and second order systems. So first order systems have this decay response where it's only an exponential decay or exponential growth. And in this case of exponential decay, these are the definitions for it, where you have the time constant, rise time, and settling time. And then for second order systems, you get possibility of decay, or exponential decay or growth response, oscillation response, or a combination of the two, where you have exponential oscillating growth decay or exponential oscillating growth. And then we derived the general solution. And then there are 4 different cases for second order system response. And we derived the general solution for a step input for a second order system that is underdamped here, which is in purple. And then we defined I guess, the performance criteria of it. So we defined the peak time, percent overshoot, which is the maximum peak incurred during the overshoot process, settling time, and rise time. One thing about the rise time is that there's no analytical equation for rise time. The rise time is dependent on the damping ratio and the natural frequency. So this graph here on the y-axis, it's your rise time multiplied by their natural frequency. And then this x-axis is your damping ratio. And what you do is you determine the natural frequency of your system, you determine the damping ratio, and then from there you can determine the rise time. If the damping ratio falls in between like these two values, like between 0.3 and 0.4, for example, you would interpolate. Okay, so today we're going to be talking about high order systems or mainly other systems. So systems with zeros, systems with a positive zero, and higher order systems. So real systems are generally higher order. And so then when we go to higher order systems, we cannot use system performances from what we define on first order and second order systems to, like, I guess, predict an accurate behavior. So for example, here we have a transfer function with n poles. So this is an nth order system, and we can't really predict what kind of response it's going to have until we know more about the poles. But we can approximate higher order systems as second order systems under certain conditions. And actually, before we continue on, one thing I want to note about this is that all higher order systems can be added up as a sum of partial sums. So you can have S plus P1 plus K2 over S plus P2. And then maybe we have a pair of complex conjugate poles, K2S plus K3 divided by S squared plus 2 zeta omega n S plus omega n squared. Now maybe I'll call this 1 for the first pair. So the point is that all of these higher order systems can be broken down into a sum of first and second order systems, which is nice because moving on to the next point is that we can approximate how the system behaves as a reduced order system. Specifically, the textbook likes to just use second order system approximation. I personally believe we can actually also do first order approximation under very, very certain conditions, but we'll just cover the textbook's approximation. So higher order systems can be approximated as second order systems under certain conditions, where if we have this transfer function and we have this single pole at minus alpha, and then you have a pair of complex conjugate poles here. Assuming we have a step input, we can do partial fraction expansion. And then once we take the inverse Laplace transform, we get some generalized form right here. So then depending on the pole location of the third pole, like the real pole, and depending on the pole location of your pair of complex conjugate poles, your response will be dominant in terms of you'll see more of the single pole response, or you'll see the pair of complex conjugate poles responding, or a combination of both. So what I mean by that is, like, let's say here, this single pole is really close to the pair of complex conjugate poles. So they're close. And when I say close, close by the x-axis. This is close here. Then what's going to happen is you're going to see the decay of both pole 3 and the decay of pole 1 and pole 2 being close to each other. So both of their decays will decay and disappear at a similar amount of time. So then case 1, we see this kind of response here. Now in case 2, this is further away. Is further away. we see that pole 3, because it's a very negative number, its exponential decay will mean it decays really fast. So then it's going to decay faster than the exponential decay of pole 1 and 2. So that total response, we're going to see that pole 3 value go away faster, while poles 1 and 2 will remain. So then we have this response here. And then case 3 is where we don't have that third pole. We only have a pair, we just have a second order system. And you note that in this second order system, in the blue line, case 3, the purple line and the blue line here are both pretty similar. So the point is, case 2 might be a case where we can use second order approximations, say that this third pole is pretty far away from these two poles where it acts like case 3. Okay, so then what this rule is saying, or the textbook says, if the closest real pole is 5 times further to the left than the dominant complex conjugate poles, then we can use second order approximation. So if we were to summarize that, let's say we have a pair of complex conjugate poles here. And this is distance A. And then we have our closest pole right here. And this distance is B. We want B to be 5 times greater than A for second approximation to hold. Dominant meaning that this is the closest to the origin. To the origin on the x-axis, on the real axis, Let me label this axis. So this is real, this is imaginary. And so that's what the textbook says. This is a very generalized rule, so it doesn't always hold true. It assumes the extra poles are real. So if you have 2 pairs of complex conjugate poles, it kind of is not, it's not as good of an approximation. And it's based on the results of adding a third extra pole. If you add maybe 4 or 5 extra poles, it just gets kind of dicey. It's very generalized. So it goes back to the statement of all models are wrong. So however approximation can be useful, and sometimes it is useful. So the reason why it only it assumes the extra poles are real because it does the approximation based off of the decay rate. So we only consider the real axis only. So we only consider the distance on the real axis. The distance on the real axis because that's going to determine how long that response lingers there before it disappears, because it only affects the decay rate. One kind of one thing I kind of noticed that I think is also sort of valid that the textbook doesn't talk about. So this is my observation. So don't sue me. And I noticed this a lot in PID design. Uh, let's say we have the opposite. Now we have this scenario. Our response might look like this. It might like look like that. And this is specifically in the case of PID design. So we see this kind of oscillation, like a little local peak, like a little local, when I say very local overshoot, it's not actually an overshoot because it's still below the final value. And then it decays like a first order system because the second order response is decaying. So that oscillation goes away really fast. But that first order decay is, or that first order pole, or that first pole close to the origin is still decaying much slower. So you might be able to use this, might be able to approximate as a first order system. And you'll observe this kind of response. This is typical in PID, typical in PID controller. PID systems. Where we see this like little overshoot, local overshoot before decaying to the final value. Of course, if I were to tune my PID controller, I could kind of get rid of that little local overshoot with some tuning, but you'll see this in PID design. Not PD or PI, but PID specifically. All right. The thing about this approximation is that it's kind of useful. It was kind of useful like 30 years ago. We don't really care about that now because we just have computers to simulate these responses. But I guess on exam, it's useful. So, okay, so now that we're done with higher orders, there's a question online.
Yeah, just a quick question. Just a quick question. So you
All right,
said
hold
that we
on.
might be able to use a
Let me check my audios. Are you speaking now, Xander?
I am speaking. Yeah, can you hear me?
I don't think I can hear you. Yeah, I don't hear you. I don't see your mic going off. Can you type in your question instead? Oh, you wanted to ask why this is first order approximation instead of second order for PID. Yeah, so maybe this is jumping the gun, but in PID systems, when you add a PID controller, what you're doing is you're adding a pole really close to the origin. So you're adding a pole basically right here. And because of that, it has a very slow decay. That's why you see that kind of response. So you actually might see it with the PI response because it's specifically the integral part of the controller that adds a pole really close to the origin. But when I say PID, it's because the derivative part of the controller will also increase the system order. So you're guaranteed to have a higher order system with PID controllers. Hope that answers your question. So we'll talk more about that in chapter 9, I believe. It's compensator design. But for now, that's just because a pole is added. Maybe I'll just say a pole is added close to the origin. So then that becomes the dominant pole. That becomes the dominant pole. So the dominant pole is going to be the pole that's closest to the origin. That's why I don't really like the textbook's definition, because it says it's going to be the dominant pole is the complex conjugate poles closest to the origin. But I think the dominant pole is actually the pole that's closest to the origin, be it a single pole or a pair of complex conjugate poles. So all right. So then let's go look at adding a zero now. So we talked about poles, but we haven't talked about zeros. Well, adding a zero will affect the magnitude and transient response. And I have an example here to show you why that's the case. So let's just first look at this system where this G of S is equal to Y of S, which is our output, divided by our input. So then if we look at the output Y of S, we get G of S is equal to U of S, so nothing special so far. So then now if we add a zero at minus alpha, let's redefine the new transfer function H of S as the zero added at minus alpha multiplied by G of S. And all of that it's just this. It's just going to be S plus alpha, or S. Oh, I see a little error. This should be alpha. S plus alpha divided by S squared plus 2S plus 2. So then the output response for H of S, so maybe I'll say Y of H here is equal to S plus alpha multiplied by Y of S. We good so far? Just a little substitution trick. All right. So if I were to take the inverse Laplace transform of Y of H, which gets us YT, or Y of H in the time domain, that's going to be equal to, I'm going to write this out again, inverse Laplace transform of, I'm going to multiply S and Y. So you get S, Y of S plus alpha Y of S. And then when I take the inverse Laplace transform of that, I get Y dot of T plus AY of T. Because this is the derivative in the S domain. And then this here is just scaling of Y of T. At steady state, Y dot is 0 because the derivative is 0 at steady state because nothing's moving. So then we just get we get alpha Y. Sorry, this should be alpha. In my notes, I have A. So then basically what's saying is our output is dependent on the derivative and on the position. And I guess this is a sneak peek into derivative control, but PD control known as proportional derivative control. PD control uses both your position and your derivative as feedback. The reason why it's called derivative control is because it's looking at the change of your output. It looks at something that's changing. So the faster something changes, the more aggressive that control will be to counteract that change. So that's why PD control is actually very useful for things that change really fast and you want a very rapid response to counteract that change. It's so it looks at so what PD control does is it adds a 0 to your system and it uses the derivative as its feedback. And so proportional derivative control uses the derivative as feedback. And adds a 0. So I kind of like to think of it as like some constant k derivative multiplied by s plus pd, d for the derivative control. You don't need to know that now, but this is kind of looking ahead what zeros are. So in a way, we use it more for math. I don't think there's a physical intuition for it. We just use zeros as a way of changing the transient response time and also scaling the size of that response with the location of the 0. So this is just an example of the application of a 0. And this is and for PD control, all the zeros are for PD control. Zeros are negative. Always. You do not want a positive 0. So positive zeros are actually quite annoying to deal with. And there are systems with positive zeros which will affect how a system responds. So even if we have a second order system, but we have a positive 0 a positive 0, it will completely mess up the response of that second order system. It's not going to make it unstable, but it's going to make it behave kind of erratically. And I'll show you an example. So we're going to talk about so the location of the 0 does not affect stability, but when we do have a positive 0, it's called a non-minimum phase 0. So a non-minimum phase 0 is a 0 that is positive. So then maybe likewise, I should include down here as a definition. When you hear something called a minimum phase system, it means that it has a negative 0. So if I say the system is minimum phase, that means all the zeros are negative. But if I say the system is a non-minimum phase system, it means there's at least one positive 0 or more. So systems that have a positive 0 are non-minimum phase systems. This means that the inverse of that system is unstable. So if I were to have a non-minimum phase system and I were to invert it, that 0 becomes the pole and that becomes a positive pole, and that means that system's unstable. It's not very useful. The reason why we invert these systems is for other controls classes like feed forward, where we take plant inversion. If we were to do a kind of disturbance observer design where we're trying to estimate the input of our model, we would take the output measurement, put it through our model and get the input, but that model is going to be the inverse. And if the inverse of that system has a positive 0, that inverse is going to be negative and that won't work. So it's it's annoying to deal with. We'll now look at an example where if we have a positive 0, so let's say we have y of s multiplied by, let's say we have alpha, but it's alpha minus s now. So that means we have a pot where alpha is positive. Then there's a 0 in the right half plane. Okay, so let's take the inverse Laplace transform of this. And we get alpha y of s minus, oh, sorry, should be alpha y of t minus y dot of t. So what we're seeing now is we're seeing a negative derivative. And usually what this kind of response will be is you have, so we're still going to have, let's say the system is stable, then our transient part, which is y dot, will go to 0 eventually. So we have alpha y of t here, or maybe better say like alpha y at steady state. And in red, I'm gonna draw the response, and it's going to look like this. And this is maybe a second order system with a non-minimum phase 0. So if I write, so NMP is usually the initials for it. So what you see as a initial response is it's going to go negative because of the negative derivative. So even if the change is positive, then the output's going to be negative. That initial value is going to be very small. So y of t is going to be very small compared to the magnitude of y of t. So maybe I'll say y of 0 plus, so it's slightly after 0. It's going to be, the magnitude of it is going to be smaller than the magnitude of y of 0 plus. That's why we see this negative dip, but then eventually the value of y grows bigger than the derivative, and the derivative is going to drop in value, like it's going to decrease in magnitude. So then what we're seeing once it becomes positive is that y is larger than y dot in magnitude. So non-minimum phase systems do exist. So non-minimum phase systems do exist. One I talked about briefly is bicycles, where when you turn right, it initially goes left, then tips right. If anyone wants to try that, you push right, it's going to turn left. The wheel is going to turn left. So then it's going to go left very briefly. You might not even notice it. Then it's going to tip in right. That's kind of this response we see. Vertical takeoff and landing aircraft are also non-minimum phase system. Vertical takeoff and landing jets. So VTOL have the same issue. So the reason why this is an issue is because we have this kind of like lag. It's not really a phase delay, but it kind of lags because we don't want it to go the opposite direction. If we're telling it to go right and your system goes left first, that's not really what we want. So this is a performance issue. Maybe an example, and it's not modeled like a non-minimum phase system, is like if you're parallel parking. Anyone ever parallel parked a car? Yeah. Yeah. So like, especially in Seattle, you cannot avoid it. what you're doing is you're turning your, if I'm trying to get into the spot here, we turn our wheels. What, we turn it right? Yeah. And we're going in reverse. And if I were to draw the center mass, like center of gravity of this car or the center of this car here, what's going to happen as we reverse is we actually swing out before we kind of go in. Well, it's a terrible job, but you get the idea, right? So it kind of looks like a non-minimum phase system where you go out, you swing out initially, then you go to your desired position. And it's not exactly a non-minimum phase system, but it acts like one. Okay, so I guess some takeaways with this section is that poles affect your stability. So a system with one positive pole will cause instability. Second order system have 4 types of responses, and dominant poles are closest to the origin and are complex conjugate poles. I'm just going to put, this is a textbook definition. These are not my words. Second order approximation can be assumed that the non-dominant poles are 5 times further to the left than the dominant poles, and this is with caveats. And it goes back to the point that all models are wrong, but some are useful. This is also just textbook definition as well. I think it really depends on these approximation, and I actually think they're kind of outdated. Now with MATLAB or Python, you can just simulate these things. You don't need to do approximation. I do have an example that I think I'll just post instead on solving on second order performances. It might help you with your homework for this week. I'll just post it with these notes instead. It's with the written steps. And I'll also finish the derivation on this lecture slide. So I'll post that after the class. Instead, I'd rather go over MATLAB code I have written up for you guys. Yeah, I have this uploaded already. So I'm going to just show you what non-minimum phase 0 will look like, and as well as system with zeros. Let me run this section. So here I'm going to run this step of the simulation, and basically what it is, it's going to be system. Okay, it's going to be a second order system with zeros at different locations. So the first system I'm going to run is our second order system without zeros. Second one's going to have a 0 at -4. Third one's going to have a 0 at -7. Fourth one's going to have a 0 at -10. Here I define my transfer function, and I list the numerator value and then the denominator polynomials, and then I use step to simulate it and then to plot it. And then I do a for loop to just repeat the same steps, but then this time with the zeros. One thing I do is I do normalize the zeros. So maybe instead I'll first run it without the normalized step response. And I'll show you the difference. So here you're going to see our system response with, move that box there. You're going to see the system response with no zero, which is the blue line right here. You can see the peak overshoot kind of occurs later than the 0 at -1. The 0 at -4 and the 0 at -7 and even the 0 at -10 all have a similar overshoot time as the system with no zero. And it's kind of hard to compare because, like I said, zeros also scale the size of your output. So if I were to normalize the step response, so I just divide by the value of the 0 here, then you can see a better comparison of how zeros affect your system response. And you can see that the peak all occurred earlier than the system with no zero. So in a way, it does increase the transient response time. One little tidbit about this is you can use step info of your system, and it'll give you the performance metrics. Let me minimize this. There you go. Step info of T. And you can see the rise time, transient time, settling time, settling min and settling max. Actually, I don't know what those values are. Percent overshoot, peak, and peak time. So step info will give you the performance parameters. So actually, I'll update my code now because I changed it. So that's an example of your system with zeros. Now, instead, let's say we have a non-minimum phase 0. So here we have a non-minimum phase at -1 or at +1. So 0 at +1. And this is a system without 0. System with no 0. So the red line is the minimum phase system. The blue line is the non-minimum phase system with a 0 at -1 or at +1. So you can see this negative response before converging. And you can see the same systems, or same poles, but now you can see the transient response has been affected. Settling time is slower. Peak time is slower. Percent overshoot is higher. Not good, basically. Okay. And then here's example with system with response with additional poles. Now what I'm doing here is I'm adding poles at different locations. And so here I have a second order system, which is in blue. Red is a pole at -1. So this pole at -1 is the dominant pole, or it's more dominant than the two complex conjugate poles. So you can see this decay. This is a lot slower. But then the pole at -3.5 and the pole at -6 all decay a lot faster. So they're more similar to the second order system. Maybe I'll even do I don't know, 3 and 9 instead and see. Yeah, so pole at -1, -4, and -7, you can see the differences. All right, and then here are just some tricks. I think I've already had these uploaded from a previous slide, or from a previous code, but yeah, here are some additional tricks. Are there any questions? I hope I'm screen sharing. Yeah, I am. Okay, good. Am I sharing two screens at once? Okay. All right, so that's the end of that section. I'm going to jump over to stability now, which is on chapter 6, and I guess we'll just get started on that. So we talked a lot about stability already, but now I will formally define stability. If I have the lecture slides right now. Okay, maybe I don't have the lecture slide. All right, I'll just talk about it because it's more about we're just going to define some definitions, and I'll just get started. I'll share my screen right here instead. All right. Oops. Let's go back page. All right, so stability is on chapter 6, and I guess the purpose of this chapter is to learn the formal. So we talked about stability, but now I want to introduce you the formal definitions of stability in linear time invariant systems. So these are just fundamental definitions of stability. There is some nuance. chapter 6 covers Routh-Hurwitz criterion, but I personally think it's outdated and not useful. And clearly, the electrical engineering professor the other day also said it's not useful at all. So that validates cutting this out. I never liked teaching it, and I never saw the purpose. So you're the first class that is not going to be that's going to skip this. So I do have it in this lecture slide anyway, if you're curious on what it is, but it's not useful. Instead, Lyapunov stability is more useful, but that's covered in ME 547, ME 583, which is nonlinear control, ME 550, which is nonlinear optimal control, ME 594, which is robust control, and possibly more control classes. That depends on the professor that is teaching it. Other methods of checking stability, which is going to be covered in chapter 10. It's Nyquist stability criterion, and using gain and phase margins. Those are much more useful than the Routh-Hurwitz criterion. The problem with the Routh-Hurwitz criterion is that you assume that stability is based only on the poles, but stability can also change with a phase delay, which is not accounted for with poles. And also, it's just like very rigorous because it's just a hand calculation used back in the day when people didn't have calculators. So we're going to go over some definitions first. And basically, the three goals for control system design, first is to control the transient response. So the transient response is something we looked at in chapter 4. Second one is to check the stability and stabilize it using like compensator design. And third is to control the steady state error and calculate it. So this is our path moving forward. So we went over chapter 4, and then we're going to go over stability now. And then we're going to talk about steady state error. Once we have a stable system, do we have error from stabilizing it? One thing about feedback design specifically, feedback design, we use feedback because we use error as our source of feedback, and we want to compensate for uncertainties due to modeling error. We also want to reject disturbances with feedback design, and we also want to mainly stabilize it with feedback design. So recall that the total response is your force plus your natural response, force being your input, natural being your initial condition response. Some definitions, a system is, so this is the first definition I told you about, and we'll talk about the second set of definitions next. System is stable if the natural response approaches 0 as time goes to infinity. So we want the natural response to be 0. A system is marginally stable if the natural response remains constant or oscillates and is bounded. So that's when you have a pair of conjugate poles. And a system is unstable if the natural response approaches infinity as time goes to infinity. So the big thing to know about this page is that this definition of stability is based on the natural response. I think tomorrow I'm going to talk about the other form of definition, the other definition of stability, which is based off of the total response, which I think is a more comprehensive and better definition of stability. All right, I'll see you all tomorrow.